Okay, today we are talking about function operations. So in elementary school, the mathematical focus is operation with numbers. What are numbers? How do they work together? What operations can we do with numbers? And we find out that there are four basic operations that can be done with numbers: multiplication, division, addition, and subtraction. Then you get to middle school and you're like, okay, we've got these four operations, but hey, look, we can still use them with fractions. And that focus is kind of the same four operations for the most part, but with their fractions. Now, fractions are still just numbers, right? They're just different expressions of numbers. Then you get to Algebra 1, and you start talking about the same operations, but with variable expressions. So now we're talking about 3x plus 4x, and how do we deal with that, right? Combining variable expressions, multiplying variables, dividing variables, that kind of stuff. Then we get to Algebra 2, and we're going to use the same operations, but now we're going to use them with entire functions. So it's kind of a mixture of all the skills we've been learning. So it's just the beginnings of mathematics that you learn in school tend to be, look at these operations and look at how they can be used with every different set of things that we have, whether those be integers, fractions, variables, or now functions. For example, let's say we've got these four operations: addition, subtraction, multiplication, and division. There are ways we can write expressions showing that we are going to use functions with addition. So f plus g of x means we're going to take f of x and add g of x. Whatever f of x is, it's going to be some expression, and whatever g of x is some expression. We're going to add them together. Same thing with subtraction. F minus g of x. F of x minus g of x. F times g of x. Notice that this is a closed multiplication dot. That's going to be important later, and I'll show you why. But f times g of x, it means we're going to take f of x and multiply it by g of x. Not exactly rocket science there. And same thing with division. F over g of x means we're going to take f of x and divide it by g of x. Now, they're noting that g of x can't be 0 if we do that, right? Because I can't divide by 0. So over here we got two examples. We're saying f of x equals 2x and g of x equals negative x plus 5. So if we're going to add f plus g of x, we're going to take f of x and add g of x. We add those together, and we end up with 2x plus negative x plus 5, or x plus 5. Okay, so if you want to pause and go through these, you can. I'm not going to go through all of them. It's just taking these two expressions and adding them, subtracting them, multiplying them, and dividing them. Okay, and just working through it. Again, the only thing I'll point out is down here, we are saying this works unless x is 5. X can't be 5, because if I plug in a 5, negative 5 plus 5 is 0, and we're dividing by 0, which can't work. So when we get to division, we always have to think about our domain, and are there things we have to restrict because I can't divide by 0. Okay, so again, you can pause this if you want to look through them. I'm going to keep moving. Let's do one. Given that f of x is equal to x squared plus 5x minus 2, and g of x is 3x minus 2, find each function. So I'm going to add f plus g of x. So f plus g of x is going to be f of x squared plus 5x minus 2, and I'm going to add g of x, so plus 3x minus 2. Now I have a lot of variable expressions here, and I just need to combine all my like terms. So I've got only one x squared. I have a 5x and a 3x, so that's 8x, and then I have negative 2 and negative 2, which is minus 4. So f plus g of x is equal to x squared plus 8x minus 4. It's basically just an exercise in combining like terms is all this is. We're going to do the same thing, but we're going to subtract. So it's going to be f minus g of x. So x squared plus 5x minus 2 minus 3x minus 2. Now the one mistake that most of you will make at least once is what I have just done. What we are actually subtracting is the entire expression. So we have to have parentheses. It may not seem like it matters, but when you think about it, I have to subtract a 3x and I have to subtract a negative 2. I have to subtract a negative number, which means I'm actually going to add that 2. So it's very important that we have those parentheses. So again, let's combine like terms. The first thing I'm going to do is just deal with those parentheses so that I don't get confused by them. So minus 3x plus 2, because when I subtract a negative, I'm really adding. Now I can go through and combine my stuff. Again, just 1x squared. Now it's 5x minus 3x, so that's going to be a 2x. And I have a negative 2 and a positive 2. Those just go away, and that's all I'm left with. Okay, so for addition and subtraction, it's largely just combining like terms. Make sure that if you subtract, you're paying careful attention to double negatives, because that's going to get you. We've got two different expressions now, or two different equations, and we're going to multiply. So if I'm going to do f times g of x, again, that's a closed multiplication dot. That's going to be important in a little bit. Means I'm going to take x squared minus 7x plus 2, that whole thing, and I'm going to multiply that by x plus 4. So we're just distributing, right? So I have to take x squared times everything. So x squared times x is x cubed. X squared times 4 is 4x squared. Now I move on to the negative 7x, and I multiply everything by negative 7x. So negative 7x times x is negative 7x squared. I'm going to stack those under my other x squareds. Negative 7x times 4 is a negative 28x. Move on to the 2. 2 times x is 2x. I'm going to stack that under x so I have my like terms together, and 2 times 4 is 8. I come back through and combine all of this. So I get an x cubed. 4 minus 7 is a negative 3x squared. Negative 28 plus 2 is a negative 26x plus 8. So f times g of x is equal to x cubed minus 3x squared minus 26x plus 8. All right, let's do the division. F divided by g of x means I'm going to take my entire expression, or my entire equation f, and divide it by my entire equation g. So x squared minus 7x plus 2 divided by x minus 4. The first thing we want to do is see, can I factor the top? If we can factor the top, we should do that and see if x minus 4 is a factor up there. So I'm looking for factors of 2 that add up to 7. I'm pretty sure the factors of 2 are 1 and 2, and I don't see a way to get those to be 7. So we can't factor this. So this is going to be our simplified answer, but we have to say that x cannot be what? Think about what would make this 0. X can't be 4. Right? Otherwise we're dividing by 0, and that's a no-go. So f divided by g of x is x squared minus 7x plus 2 over x minus 4 when x is not 4. Okay, again, you can pause and look at that. I'm going to keep moving. Composition of functions. Now this is what I kept alluding to when I said that solid multiplication dot would be important. Another operation we can use with functions is the composition of function. In a composition of functions, the results of one function, meaning the output of one function, is used as the input of the second function. Okay, so if I was taking this is how we write this, and the way we say that is f of g of x. Right, so f of g of x means whatever x is, you plug it in to g. Whatever that output is, whatever value you get after you plug something in, that goes in to f. Okay, so let's say we wanted to do, just for a sidetrack here, f of g, it's not fog, it's f of g of 2, right? Which means I'm going to take 2 and plug it in for x in g. So 2 squared plus 4 is 4 plus 4 is 8, right? So g of 2 is 8. So I'm going to take that 8, and that's going to go in for f. So f of g of 2 is equal to, when I plug 8 in for this guy. So 3 times 8 is 24, minus 5 is 19. So f of g of 2 would be the 24 minus 5, or 19. Okay, we don't always have something to plug in for x, though, so we need to be able to do this when x is just the variable. So instead, we're going to take all of g and plug it in for x in f. So I take this guy and plug it into that one. Just like when we were doing substitution with systems of equations, we're going to plug the entire thing into the other equations. So f of g of x will be, I'm going to start with the first one, the thing that comes first. I'm going to start writing that, but when I get to an x, I'm going to stop. 3. Now instead of x, it's the entire other function. Then I go back and finish the first function. Right, so I start with f, and when I get to an x, I stop, and I plug in g of x. Then I continue writing f. Now I just simplify this. 3x squared plus 12 minus 5, which simplifies to 3x squared plus 7. That is f of g of x. There are two ways to write f of g of x. So I could write it like this, f of g of x, which is what we've been doing. Or, when this might make more sense, this is how I prefer to write it. It's just that the book uses this open circle here. The way I'd like to write it is f of g of x. And that really helps to sort, or to solidify the idea that I'm plugging g of x in to f of x. Okay, so this might make more sense in terms of a notation. I will try to write it that way. The book will probably write it this way. As long as you know that these two things are the same, you'll be in good shape. Okay, so the second one, whatever comes last, is the one you're plugging into the other one. Okay, I think I have another example of that here. Okay. What I mean by there's a better way is if you're doing a number, if I'm plugging in like the 2, right, and I figure out what it is for g first, and then I have to plug it in for f, the better way is to just do it all at once and sort it out to be this guy, right, because that teaches the computer what to do in one step instead of saying, hey, computer, plug 2 in for this and get an answer, and then take that answer and plug it in up here. To a computer, that takes a lot of time. So a computer much prefers having just the one expression to say f of g of x is, what was it, 3x squared plus 7. 3x squared plus 7. That way, you can do that all at once. If I plug in the magic 2 in here, like we had in that made-up example from before, 3 times 2 squared plus 7, well, the 2 squared is 4, times 3 is 12, plus 7. What's that? 12 plus 7. Hey, that's the same 19 we got earlier when we did them one by one. So that's just kind of proof that you can do them one by one, or you can compose the functions into one new composite function. Okay, so I want you to try this one on your own. Go ahead and pause this and try this one by yourself, and then unpause it, and I will show you how I do it. Okay, first thing I want to remind you of, this could be written like this instead. Right, f of g of x. So I'm going to take g of x and plug that in for x in f of x. So f of g of x is x squared, but instead of an x, remember, I'm using this x minus 6. So x minus 6 squared plus 2. F of g of x is equal to x minus 6 squared plus 2. Obviously, we have to deal with that first. We have to multiply that by itself. So don't go x squared minus 6 squared. Remember, that's x minus 6 times x minus 6. We have to distribute. That's x squared minus 12x plus 36. And then I still have this plus 2 hanging out. Simplify that, combine my numbers, and I get x squared minus 12x plus 38. That is the composite function f of g of x. If we went the other way around, we would get something else, right? So this is not like multiplication. F times g and g times f, those would be the same thing. But f of g and g of f are not the same thing. So the order matters in terms of what's the inside that you're plugging into the outside. That makes a difference. Okay. Hopefully that makes a little bit of sense. You're on to the homework. Good luck.